Welcome back. In this lecture, we'll see the interrelationship of electric field with electric potential. We'll prove that electric field can be defined as negative gradient of electric potential. Let's see how can we do that. The first aspect is that we have already proven that work done per unit charge was defined as electric potential, and that turned out to be E dot dr integration. That is, you may say that potential is basically line integral of electric field. Let's see if the converse is also true. Can I define electric field in terms of electric potential like that way? Let's see. Consider a charge and it is being pushed across. I am assuming both the charges to be positive, and it is being pushed across towards the Q node, is being pushed across towards Q with a force of repulsion, and the force of repulsion is acting away from this Q node in this direction, and the displacement is in this direction. I can say that small work done dW is equal to F dot dr, and it is easy to write it down as Q naught times E dot dr, as we know that electric field is force per unit test charge. Therefore, I may write it down as minus Q naught E dr, as angle is 180 degrees. We also, while doing this article, had proven that work done is basically charged into V1 minus V2. So it is easy for me to write it down as dV. Work done is dW. dW I may write it down as equation number 2. Let's equate equation number 1 and 2. Minus Q naught E dr is equal to Q naught dV. The Q naught and Q naught get cancelled. E can be defined as negative gradient of potential. E is equal to minus dV by dr. Electric field can be defined as negative gradient of potential. Gradient, the word gradient basically means variation in something with respect to normally spatial coordinates, or you may say variation of something with respect to distance. This is the simplest way of defining it. So as I am going, let's say this plate is positive, this plate is negative, and we say that there is electric field existing in this direction. Electric field is existing in this direction. Then what is potential? You may say that as you are going along the field, the potential is continuously changing. The positive is at high potential, the negative is at lower potential, and as I move across this region, the potential is decreasing. There is a variation in potential with distance, and since it is decreasing, that is signified by this negative sign. So electric field always points in the direction of decreasing potential. I repeat, electric field always points in the direction of decreasing potential. Now, it can be an interesting question to discuss based on this. Let's say I have been given various cases like this. Case number 1, this is point A, this is point B. This is case number 1. Case number 2 is opposite to it. Let's say this is point A, this is point B. I discuss case number 3. Let's say it's something like this. Point A and point B, and one more case. Say, what should I do? Let's say it's the electric field is okay. This is enough. 3 cases are enough. In this case, what is the relation of electric field at point A and electric field at point B in magnitude? And what about their potentials? I want to see the relationship of electric fields at point A and B and electric potentials at A and B. In this case also, I wish to find out the same relation, VA and VB, and in this case as well, I wish to find out the same relationship between EA, EB, VA and VB. I could have written more cases reversing the electric field, but I think the idea would be clear in these three cases only. Since electric field is pointing from that side towards me, that means the field lines are going from A to B. I have already told you that electric potential decreases if you move along the field. Electric potential decreases if you move along the field. So no need to be confused that in any case, since in all the cases electric field is going from A to B, from A to B, from A to B, electric potential at A is greater than electric potential at B. Electric potential is greater than electric potential at B. Electric potential at A is greater than electric potential at B in all these three cases. Had the field been reversed on the other side, you could have formed a different relation. But what about electric field? If field lines are crowded, the field is stronger. If field lines are spread out a far distance away from each other, then electric field is weaker. At this point, electric field at A is less than electric field at B. Electric field at A over here is stronger because the lines are crowded. So electric field is greater at A than electric field at B. And in this case, since the lines were uniformly separated from each other, the electric field at A is same as electric field at B. In the next article, we'll discuss what are equipotential surfaces, what are equipotential surfaces and what are their properties. Thank you.